Hello again. This is Math 2232 coming to you from the College page. And this is part 2 of the lecture we started earlier, the area between curves. As always, please be attentive listeners while watching this video. So we're going to talk about the area of a region between two curves. So we'll find the area of a region between two curves using integration, and we'll find the area of a region between intersecting curves using integration. So with a few modifications, you can extend the application of definite integrals from the area of a region under a curve to the area of a region between two curves. So if you consider two functions, f and g, shown here, there is f and there is g, and they're continuous on the interval AB, and both of these graphs, for now, lie above the x-axis, and the graph of g lies below the graph of f. So this is what's happening in the picture. So you can geometrically interpret the area of the region between the graphs as the area of the region under the graph of g subtracted from the area of the region under the graph of f. And in fact, this shows this is the integral from a to b of f of x dx. That's the area under f. And this is the area under g. And that's the integral from a to b of f of x dx. And so if you subtract the two, you get the area of the region between f and g. Now, it is useful often in these problems to think about sketching a representative rectangle of a certain width. In this case, we're doing delta x, and showing the height, and this allows us to think about the area of the representative rectangle. So here what you're doing is you're drawing the representative rectangle, and you can see that if you add the rectangles together and take the limit as the norm of the partition goes to 0, which is, implies that n goes to infinity, you can obtain this Riemann sum, and this actually the integral from a to b. And so we have then this result, the area of a region between two curves. If f and g are continuous on AB and g of x is less than or equal to f of x, then the area of the region bounded by the graphs of f and g and the vertical lines a and b is the area is the integral, definite integral, from a to b of f of x minus g of x dx. We're taking the larger values minus the smaller values. Now, it does not require that they're both above 0 there, because if you look at this and think about the pictures that you're drawing and the definition of the definite integral, even though g of x is below the axis here, when you integrate, you'll get a negative area of that, and you can see that these vertical bars will add up to a Riemann sum, and you take the limit as n goes to infinity, so it works even if something is below the axis, as g of x is here. So you see the same formula is going to work. So the height of the representative rectangle is f of x minus g of x, regardless of the position to the x-axis. Now, representative rectangles are used throughout this section and in other applications of integration, and so I encourage you to draw them. They help you to realize if you're integrating with respect to x and or y. And so a vertical rectangle of width delta x implies integration with respect to x, and a horizontal rectangle of width delta y implies we're integrating with respect to y. Now let's look at an example. So what we're going to do here is we're going to try to find the area of a region between two curves. Find the area of the region bounded by the graphs of y equals x squared plus 2, y equal negative x equals 0, and x equal 1. The first step, of course, is always to graph this region. So here's a graph of this region. Here is f of x equal x squared plus 2, and here is g of x equal minus x, and we draw our representative rectangle. And so you see that the area of this region then is going to be, the area is going to be the integral from, we're going from 0 to 1 by the definition of the problem. And this is f of x, which is the upper function. So that's x squared plus 2 minus. And please understand, my dear students, this is going to be minus the whole of g of x. So in this case, it's a minus, which makes that a plus. Now, so what we're going to have then is x squared plus x plus 2. So we add 1 to the exponent divided by the new exponent for 2 of those, and the other one is 2x. We evaluate it using the fundamental theorem of calculus from Calc 1 from 0 to 1, and we plug in the numbers, and we get 17 over 6. Let's look at another example. Here, we want to find the area of the region bounded by the graphs of f of x equal 2 minus x squared and g of x equal x. Again, the first step is to graph these functions. And here's what we get, and we draw our slice, getting this. So now what we're going to do is we're finding this area that is shaded in pink here. Now, we have to find the points of intersection to have the limits for the integral. So this goes back to algebra. So to find the x coordinates, and again we're integrating dx because of that slice, set f of x and g of x equal to each other. We get this, and then we move everything to one side to get this, and this will factor, and we find out that x is equal to minus 2 over here, or x is equal to 1. Those are the limits of integration. And so the area of the region is, we integrate from minus 2 to 1 of, this is the top one, that is 2 minus x squared, minus the whole of the bottom one, and we integrate again, do the calculation using the fundamental theorem of calculus, and we get 9/2. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself, because self-care is important, and take care of each other because we're all in this together. Look forward to seeing you in the third and final video of this lecture.